Hello friends, welcome to the series of videos on the course The Integral Equations. In the first video, we have seen the basic definition of integral equations and some basic examples. Now in the second video of integral equation, we will see the classification of integral equations. Now this video may go a little longer because I will take a particular definition and I will take around 2-3 examples related to the given definition. So let's get started. So to classify the integral equation, please excuse for the spelling of equation. So to classify the integral equation, the general form of the integral equation, and of course I am talking about the linear integral equation. Non-linear integral equation, it will be like y square, or this y term, this y of x is the unknown function, that will be a non-linear term. So the general form of integral equation is given by vx into yx. Now again I repeat, this yx is the unknown function. So vx into yx is equals to fx plus lambda integral from ax to bx kxt yt dt. So now in this case our function vx, fx, ax, bx, kxt are all known functions of x, and this y of x is the unknown function, and this lambda is a real or complex constant. This function kxt is a function of two variables x and t, and that is called kernel of integral, this given integral equation. Generally, the integral equations are classified into first kind, second kind, and third kind. Now let us check what is first kind, when the integral equation is called the integral equation of first kind. So this integral equation is called the integral equation of first kind if this known function is equals to 0. And in that case, if this v of x is equals to 0, then our integral equation of general form becomes fx plus this lambda integral from ax to bx kxt yt dt, and of course that will be equals to 0. So this form of integral equation is called the integral equation of first kind. So let us see some examples of the integral equations of first kind. Of course your vx should be equals to 0. So in that case, let us take this e raised to x is equals to integral from 0 to x y of t dt. Now in this case, my unknown function y of t is under the integral sign. This is your fx, and this unknown function does not appear outside the integral sign. That is the another way to say the integral equation of first kind. For second example, say integral from 0 to x xt yt dt is equals to say 10. And let us take one more, third example. Say integral from 2 to 5 sine x plus t yt dt is equals to say cos x. The second kind of integral equation is your function vx is equals to 1. So of course the general form of integral equation takes the form yx vx is equals to 1. So yx is equals to fx plus lambda integral from ax to bx kxt yt dt. Let us take some examples. For example, y of x is equals to say 1 plus integral 0 to say 3 x square plus t y of t dt. Again I will say we are talking about the linear integral equations. Another, let us say y of x is equals to integral 0 to x square xt yt dt. And let us go all the definitions with three examples. Y of x is equals to 10 integral say 1 to x cos xt yt dt. Next is the integral equation of the third kind. Also it is called the integral equation, or also it is called Kalman type. So in this general form, this Vx is not equals to constant, or I can say it is not equals to 1. That constant that should not be equals to 1. So for this kind of for this thing, let us take straightforward here examples. Say x y of x is equals to lambda x to x square x plus t y of t dt. Another example, say sin x into yx is equals to cos x plus lambda 0 to 100 t yt dt. And the last, say e raised to x y of x is equals to sin square plus 2 x to square root x x square t raised to 3 yt dt. So these are the examples of the integral equation of third kind. So the next classification comes or is the integral equation which is homogeneous or non-homogeneous integral equation. So the integral equation in this general form is called homogeneous integral equation if this function fx is identical equals to 0, and if it is not, then we call it as non-homogeneous integral equation. For example, y of x is equals to 3 integral from a to b, say kxt y of t dt. Now in this case, though I have written a and b, these a and b are constants. So y of x equals to 3, a and b are constants, kxt again I have taken general kernel, y of t dt. For second one, y of x is equals to, say, integral from sin x to 2 t square yt dt. The only care you have to take is that this function has to be 0, then it is called homogeneous integral equation. Next, and the most two important things are the integral equation, which is called Fredholm integral equation, and another is called Volterra integral equation. We'll come to it. So the integral equation is called Fredholm integral equation if these limits, this ax and bx, are both constants. And to take examples, we have Fredholm integral equation. So say x square y of x is equals to x plus 4 integral. These should be constants. That's how you define your Fredholm integral equations. So say 3 to 4, we may have some kernel, say xt square y of t dt. So say y of x is equals to integral 0 to, say, 0.5 x plus t yt dt. And the last, let us take integral 0 to 6 y of t dt equals to 0. So again, though we have said it's a Fredholm integral equation, we may further say that it's a non-homogeneous Fredholm integral equation. We may say that it is the integral equation which is Fredholm integral equation of third kind. So those classifications are also there. And the second one is Volterra integral equation. So the general form Vx by x equals to fx plus lambda integral from ax to bx kxt yt dt. Now again, it is based on the limits of the integral. As in the last class, if ax and bx are both constants, it is called Fredholm integral equation. And if either ax or bx or both are the functions of x, those are not constants in fact, so such a kind of integral equation is called Volterra integral equation. For example, say 3 plus x yx is equals to 10 plus lambda integral. Now this classification is based on the limits of the integral equations, these integrals. So this either lower limit or upper limit or both should not be constant. It should be a function of x. So let us take 0 to x. Then this is your kernel, say t yt dt. So based on this, we can say this is third kind, this is non-homogeneous, this is Volterra. And based on the kernel, we will come in the next few minutes. Second example, say yx is equals to cos x plus integral x square to 10 sin x plus t yt dt. And for the third example, sin x is equals to integral x to x square yt dt. So these limits are the functions of x, so it is Volterra integral equation. Then the unknown function just appears under the integral sign, so it is homogeneous. It is first kind, and there is again a function here, so it is non-homogeneous. The next classification is the integral equation, which is singular integral equation. For this classification, what we need is either this ax or bx is infinite, or the kernel becomes infinite inside or at some point in the domain. Then the integral equation is called singular integral equation. I repeat, either this lower limit or upper limit has to be infinite, or the kernel becomes infinite at some point in the domain. Then the integral equation is called the singular integral equation. For example, first one, say y of x is equals to fx. Again, this classification is based on the limits of the integral or the kernel. So integral from 0 to infinity, some kernel kxt, general kernel I am taking, yt dt. And let us take one more example wherein your kernel becomes infinite. So y of x is equals to integral 0 to x, say 1 upon square root x minus t yt dt. Now here, though your limits are not infinite, but at t is equals to x, your kernel becomes infinite. So this is the example of singular integral equation. Another classification is based on the kernel. So for the kernel kxt, the kernel kxt of the integral equation is such that it is a function of single variable x minus t. So wherever there is a kernel, if we can write that kernel as a function of single variable x minus t, then the kernel then we say that kxt is said to be a kernel of difference type, or we can say it as a convolution type of kernel. We can go for very simple example. What we need is your kernel has to be a function of single variable, or in short, we can write the kernel as a function of single variable. So yx is equals to x plus integral 0 to x. This kernel has to be a function of x minus t, not as such a function of x minus t, but you can write that kernel as a function of x minus t. So very simple thing, I can write x minus t the whole square. So this kernel can be viewed as it is a function of just one variable x minus t. You can write integral 0 to 5 or 0 to 4, say sine x minus t yt dt is equals to 5. So your kernel is sine of x minus t, and we can view this is the sine of u where x minus t is equals to u. It's a function of just one variable. And lastly, say x yx is equals to lambda integral x to x square sine x plus t yt dt. But again, be careful. Here your kernel is sine of x plus t, and this kernel cannot be written as a function of one variable x minus t. So sine of x minus x plus t. So this kernel sine of x plus t is not the kernel of difference type or convolution type of kernel. Another classification based on the kernel is a separable kernel or degenerate kernel. So again, the kernel kxt is called separable kernel or degenerate kernel if we can write this kernel kxt as a finite sum of product of two functions, one function a function of x only and another function a function of t only. So mathematically we can write this as kxt is equals to, it should be a finite sum. So say let me take I from 1 to n number of terms are there, then a function of x only and a function of t only. So this kxt has to be a finite sum of product of two functions. One function is a function of x only and another function should be a function of t only. Then this kind of kernel is called a separable kernel. And to see the examples, the kernel kxt is equals to say x square t plus x t square. Now if you note here, this kernel is a sum of two functions. Now so it's a finite sum, and this function is a function of x only and t only, So this kernel is separable kernel. Next example, say the kernel kx comma t is equals to cos x plus t. Now in this case, directly cos of x plus t we cannot say it's a separable kernel. What we can do is, you can use the formula of cos of x plus t, expand it, so you can write this as the sum of two functions, cos of x, sin of t, those expansions we have to do, and once we expand this by using the formula of cos of a plus b, you will see that this is a separable kernel. And next, last one, say sin of or k x comma t is equals to sin of xt. Again, be careful. Note that this sin of x plus t, when you expand as a series, it is an infinite series, so it cannot be written as a sum of product of two terms, two functions. So this is not the example of separable kernel. And the next classification is again based on kernel called a symmetric kernel. The kernel kxt is called a symmetric kernel if kxt is same as k t x bar. So this is a complex conjugate. So if you have a kernel in such a way that kxt is same as k t x bar, then that kernel is called symmetric kernel. And finally, let us take one or two examples and see all kinds of classifications. So for that, let us take one, or let me change the color, it is not so visible. So one, say y of x is equals to x plus lambda integral 0 to 1 e raised to x minus t yt kt. First when you see it is y of x. So in this case, when you compare this with your general form, this will be vx equals to 1. So this is of second kind. Next, when you see here, this is x is there, so fx is not equals to 0. So this is non-homogeneous. Next, when you go for the limits, this is 0 and 1, both are constants. So This is Freedom integral equation. Next, when you see the kernel, so in this case your kernel is k x comma t is equals to e raised to x minus t. So if we view this, we can say it's a function of just one variable x minus t. So we can say this is convolution type. Again, you can write this as a function of x only and a function of t only. So again, this kernel is of separable type. And lastly, if you want to see whether it is symmetric, when you say kxt is nothing but e raised to x minus t, and ktx, if you just ignore that conjugate part, ktx is nothing but the first variable is t, so t minus x, and of course these two are not equal, so this is not a symmetric kernel. And let us take the last example, second example. Say y of s, don't just go with s, x, t and all. So in this case y is a function of s, so y of s is equals to integral from 0 to s sine s minus t yt dt. Now again, if you check here, your general form vx is nothing but 1, so second kind. Your fx is 0, so it is homogeneous. Your limits, lower limit is constant but upper limit is a function of s, so it is Voltaire integral equation. Your kernel is s minus t, you can write this as a function of s minus t, so convolution type. Again, you can use the formula of s minus t, sine of, that is sine of a minus b, expand, you will see that this is separable kernel, and so on. In the next video, we will see what is the solution of integral equation, and we will see how to check whether the given function is a solution of the given integral equation. See you in the next video.